All right, let's continue the discussion of inflation. And today our goal is to compute the quantum fluctuations around this classical background that we discussed last time. Okay, so first of all, any questions about the setup for inflation? Okay, so we were considering this sort of potential for phi. I mean, the potential for inflation, no one really knows what it is, but this is just something nice to stare at that has the basic features that we need. Okay, so I'm going to imagine, and there's some nice minimum here, and then it comes up, and then is particularly flat in this regime. Okay, so it should not be perfectly flat, as I said last time. Our action, again for phi, we can write out the whole thing. Okay, this is the action for our scalar field. And again, at the level of the classical background, if you write some phi just as a function of time, you can check if you look at a homogeneous thing. Okay, homogeneous, you don't have to worry about this. So you just have a regular looking sort of kinetic term minus a potential. And rest assured, if you think about the energy or the energy density, it's just kinetic plus potential. So rho on the background is just a half phi bar dot squared plus v on the background. Okay, so as we discussed last time, if the field is kind of sitting up here somewhere and it's slowly rolling, okay, that would mean its kinetic energy is small compared to its potential. Its energy is basically almost a constant just given by v for most of this history. So the energy is approximately just v. And you see it's roughly a constant. Okay, so constant we know gives rise to accelerated expansion and all the good things associated with inflation that we discussed last time. So first of all, any clarifications about that point? Okay. So remember, this does such a good job that it leads to a universe that's accelerating so much that, like we said, if we think about phi versus position, even if I allow it to be inhomogeneous, something like this, so the field is up here somewhere, but in different points in space, somewhere it's up here, somewhere it's there, and so on and so forth. Okay, because of the accelerated expansion, this is so stretches to such giant scales that our whole universe today could just be a tiny little piece of this thing, say here. And so in that region, phi looks approximately constant. Right? It looks like an incredibly tiny piece of a function, therefore it's going to look constant in that function. Okay, so the homogeneity at the classical level is guaranteed. Okay. Good, so our task now is to think about perturbations around this. So let's think about quantum fluctuations. So I'll write phi, as I said at the end of last time. First, typically. So yeah, so just a reminder that effectively phi equals phi bar in this tiny little region, that's our whole universe. Okay, so this is what we want to think about. So in effectively our whole universe today, at least over the 15 billion light years, okay, maybe not over the e to the 100 light years, but over the 15 billion light years, it's just going to look smooth, homogeneous. And so maybe this here is phi bar at some moment in time, and it will slowly roll down, but it will slowly roll down. The phi will just slowly roll down in the same way across the whole universe. at the classical level. Okay, so our task now is to think about the fact that there can be delta phi, little quantum fluctuations around this value. And those will be inevitable from the uncertainty principle. Okay, so the action for the fluctuations delta phi, we wrote it at the end of last time. You just expand this thing to the quadratic order, assuming delta phi is small. Okay, that's the quadratic action. All right. And the way I've drawn it here, I've tried to indicate, let's even go for a potential that has a slight slope to it, but looks awfully linear. Okay. So if it's sufficiently linear, we can even throw away this second derivative term, b prime prime. Okay. Now there are more sophisticated ways of doing the calculation we're going to do today that we're not going to rely upon that simplification. Okay, I'm just going to give you the first sort of simplest way to understand fluctuations and how they convert to density fluctuations. Okay, but you see I have at least one scenario here where it's very flat and linear, where you could imagine that this second derivative is to be ignored. Okay, so this is our action, just this. Okay, just quadratic, time derivative squared, spatial derivative squared. All right. So for this thing, we're going to pass the k-space. And so our delta phi of xt, I'm just going to call that delta phi hat, as I normally do, just for the Fourier variable. And it's a function of k and t, but I'll put a little k subscript there instead of writing brackets k. So the action now, you get d3k over 2 pi cubed, a cubed, 1/2. Okay, now I'm going to put in absolute value squared, just because in general a Fourier transform can be complex. So I just put in some absolute values. And then we know that when you take gradients, right, in Fourier space, they just pick up factors of k. Okay, ik. So if you like, one way you can think about it is you get an ik from one and a minus ik from the conjugate. So altogether you get a minus, this minus sign will survive. It had better. So you get k squared. Okay, so that's our basic action. So people okay with just this transition to k-space? Yeah. Oh, yeah.
When we translate x to k-space, that's going to pick up the 2y, but x0 is still.
No, I'm just choosing to do a Fourier transform only in space. That's right. Yeah. Yeah, I'm doing a 3-dimensional Fourier transform. That's it, not a 4-dimensional Fourier transform. If I did a 4-dimensional Fourier transform, dt would become d omega. I'm not doing that. Okay. And yeah, other than that, we've basically just, like the power theorem, right? If you have an integral over space of a function squared, it equals the integral over k-space of the Fourier transform squared, is the power theorem. Let me just remind you, anyone forgotten that. So if you have d3x or some function of x squared, this is d3k, absolute value in k-space squared. So we're just using this to move from here to here. And the time derivative goes straight through. And the only tricky thing is the gradients pick up k factors of k. All right. So this you can think of this here. This is looking like a dt now of a Lagrangian. Okay? So there's, in that piece there would be your Lagrangian. And then we can relatively write down the Hamiltonian. Okay, so there's not going to be any shocks. Our Lagrangian is just a kinetic term minus this thing. So this is like kinetic minus potential yet again. And so the Hamiltonian is just going to be that plus that. Okay. Well, let's just write this for 1 second. Okay, all I did was put a plus there. When we go from simple enough looking Lagrangians to the Hamiltonian, we just get a minus flips to the plus. Right? Except this Hamiltonian is not quite written in terms of the right variables. Right? You have a Hamiltonian, you should not write it in terms of the variable and its time derivative, but at the variable and its momentum conjugate. Okay, so let's just do that. So if I try to figure out the momentum conjugate, okay, anyone have an idea what the momentum conjugate for this theory might be? So the partner of phi, yeah. It's phi dot, yeah, almost phi dot, but then there's just an a cube sitting out front. So remember, a is a proportional to e to the ht. Okay, so we have to track the a cube. So in the way I've set it up, we have a kind of continuum of points, if you like. So in this continuum, we keep the measure separate, and then this is the piece that we track. We could make everything discrete, and I will make it discrete in a minute, which may even make that even more clearer that I should not include the 2 pi's. But yeah. So the momentum conjugate pi k is just going to be the a cubed. And the time derivative with respect to the phi dot is essentially delta phi dot. Well, even with a conjugate, I suppose. Doesn't matter. All right. So I should just insert that in here. I'll call that one pi. We can call it delta pi if you like. And so the only interesting thing that has happened is because of the a cubed, when I insert here, I need to write this as 1 over 2 a cubed, right? Because I got a cubed divided by a cubed squared. So altogether we get 1 over a cubed. And then the a cubed that was there, I multiply it out here, and then this becomes a. Okay, I'm just simplifying the second term. Okay, so it's not looking that bad. And then there's a commutation relation in this continuum limit between the variable phi and its momentum conjugate, which I could evaluate as, say, k prime. And this is like, you normally think this is like I h bar would be the commutation relation. We're going to say h bar to 1 in a second, but I can write it there for now. And in the continuum limit, this picks up a 2 pi cubed delta k minus k prime. Okay, that's the measure in the continuum of k values. All right, so let's write down the discrete version of this. So my job for the next couple of minutes is to massage this thing so it looks as canonical to what the harmonic oscillator Hamiltonian as it can possibly be, okay? So we're going to go to the discrete, then go back to the continuous. So this is a kind of a step just to make it look as clear as possible. With a bit of experience, you wouldn't need to worry about this discrete step, but let's include it. So in the discrete version, right, that means I put everything in some volume of size V, and my modes K, should obey some boundary condition, and so on. So the set of K modes becomes discrete. So then this becomes a sum over the K modes instead of an integral. And then the measure gives you a 1 over volume. Okay. If volume is very, very big, your modes, you are almost in the continuum. So the step size is very, very tiny. So there's a 1 over volume. And then I just write that out. Okay. And in this continuum limit, the statement I should write here is, well, sorry, in the discrete limit, this case here is no longer a delta function, right? Your delta function becomes a Kronecker delta kk prime. And when k equals k prime, the delta function hits. That sounds like infinity, but in the discrete, when things are inside of a volume, that just picks up the volume. The infinity is regulated to a volume V. Okay. So anyhow, in this case, it's also kind of, there's no 2 pi's anymore. All right. So if I were to make things look absolutely canonical, we could even write our commutation relation there. Usually when you write, the commutative of x and p is IH bar, you don't write IH bar times a volume factor. So we can rescale, so this V looks a little awkward. We can rescale things by root V, and then the commutator is just IH bar. So I don't know, it gets a bit awkward with notation. So I'll define delta phi. This is going to be a twiddle. Okay, it's just delta phi and with some root volume factor and pi twiddle as well. Okay, I can do that. And then you see all these volume factors disappear. Okay, this will, pi squared over V is just pi twiddle squared, and so on. And the V there will cancel. Kronecker delta, not the density contrast. Deltas get used for like 10 different things in this analysis. Yeah, just Kronecker delta, 1 or 0. Okay, and the Hamiltonian is finally just a sum. Okay, I just wrote the same thing without the V's. That's all that happens. Okay. So we can compare this. Right, to, let's say, doesn't work very well. Let's compare this to say x comma p is IH bar, and the Hamiltonian half p squared over m omega squared over 2 x squared as your standard Hamiltonian for the harmonic oscillator. Okay, and then we could just do a sum. If you happen to have many harmonic oscillators, okay, you see the sum is really simple here because the different k's are not talking to each other. Right? It's just a sum over k. Just n copies of the same thing. So if I wanted to mimic that here, easily I could just write a sum over, I don't know, each oscillator I. I could put a little I subscript here. And then we could even write, to mimic this, you could just write ij Kronecker delta ij. Okay, because each oscillator is quantized with respect to its partner x and p, and when the I is not equal to j, one has nothing to do with the other, so there's no commutation there. So is everyone happy with that? So I hope you agree that this Hamiltonian that we constructed, along with its commutation relation, is identical to that of a set of harmonic oscillators that we're all hopefully familiar with. So any questions about this? Okay, so we can just read off kind of some of the answers that we need, some of the facts that we need about the states of this theory by just borrowing our knowledge of the harmonic oscillator. Right. Oh yeah, and so to continue the comparison, let's just be 100% explicit then. Right, we're saying x playing the role of delta phi, or xi if you like, pi phi k. So the quote unquote the mass, you just see is this prefactor here, a cubed. You just connect the dots, it's very simple. And then the omega here to match this, the omega has to be k over a. Oh, well, that in a way will trip us up. That's where I would need a whole nother lecture to do it properly. So yes, so this is the correct comparison, as you said, is that a is a function of t here. So correspondingly, it's connected to a harmonic oscillator with a time-dependent mass and frequency. Okay. Unfortunately, we don't have time to do that problem properly now, but we're going to state what happens when you solve the time-dependent harmonic oscillator. But you can imagine that as a little exercise in a quantum course. So what happens to the state, and we'll be talking about the ground state of the harmonic oscillator in the case in which the mass and frequency depend on time. And they depend on time in a very special way, because again, this A here is just proportional to e to the ht. Okay, so that tells you exactly how this m is proportional to e to the 3ht, and then omega is proportional to 1 over e to the ht. Okay, so they have a very particular dependence on time. All right. Okay, so the first thing we want to talk about then, all right, we have this theory or this theory, there's different variables, a different notation. We wish to think about some particular states. And so we're going to focus on the ground state. Okay, so in this theory, we want to discuss what we would think about the ground state. Okay, so let's even go back to our discussion from last time at the classical level. Okay, so for example, we had this vacuum energy, in particular the background level, right? There's this effectively vacuum energy provided by phi. And at some point I mentioned to you that, there could also be other stuff around. There could be matter, there could be radiation, even curvature. And all that other stuff, because of the exponential expansion, it just gets diluted, right? The matter goes like e to the minus 3ht. The radiation goes like e to the minus 4ht and so on. So they're all just getting depleted exponentially. So you see those additional pieces of energy on top of the background just get depleted, all right? So similarly, you can imagine that if you take this state for phi itself and you put it in an excited state, the dynamics is such that that extra bit of energy by putting it in an excited state will similarly just get washed away as the universe expands exponentially, right? It just tries to deplete every bit of extra energy it possibly can. And then the only problem is that, well, two things. It can't just wash away the classical field because it's stuck in this potential. So it has the classical V energy. And then it cannot wash away the ground state. So that's the minimum state it can get into. So does that make sense? So we could start in a generic state within reason, and the excess energy will get depleted exponentially fast. And so you'll end up in the ground state of this field. Okay, just bearing in mind that this is only the perturbation on top of the classical background. All right. So with respect to this phi bar here, our fluctuations, delta phi, some kind of ground state, but it's the ground state of the harmonic oscillator. Okay. Now, everyone knows, right? What's the shape of the wave function of the ground state of the harmonic oscillator? Goes like that. Okay. In words, what is that function? Remember what that function is? Oh, you don't remember? It's a Gaussian. Yeah, that's right. Yeah. So the ground state of the harmonic oscillator is Gaussian. That's interesting. Remember, the fluctuations in our universe look Gaussian. Okay. So the Gaussianity of the fluctuations in our universe is going to be connected to the fact that the ground state of the harmonic oscillator is a Gaussian. This is a kind of interesting thing. Okay. So Gaussian probability distributions, you meet them many times as usually, right, as they come up because of the central limit theorem. So you add up n variables, and somehow the sum of n variables under certain conditions leads to a Gaussian. Well, that's not what we're doing here. This thing is just a Gaussian, straight off the bat. Okay? It's not because they summed n variables and it washed out and looks approximately like a Gaussian in some large n limit. No. The ground state of the harmonic oscillator is just a Gaussian. Now, the ground state of this theory is similarly a Gaussian because it's the same Hamiltonian. Okay. So that's a big deal. Now you could imagine, therefore, complicating inflation, having a more complicated model, and getting departures from Gaussianity. Okay, and so you can do that because, again, it's not appealing to the central limit theorem. So, but for simple models of inflation with some nice smooth potential, like I've considered, this is going to be a Gaussian. It doesn't need to be flat per se; it just needs to be kind of smooth in some sense. All right. Yeah, so somehow our fluctuations, that's the wave function. Okay, so the wave function of x, let's say the wave function squared, is proportional to the exponential minus x squared 2 over its variance. And then, so therefore, for this theory, psi of, I don't know, delta phi k squared is proportional to exponential minus delta, yeah, delta phi k squared, I guess with a twiddle, over its variance. Okay, anyway, so you know what I'm trying to write. It's crammed it in the corner. It's just a Gaussian with some variance. Is that okay? So we have to write down the variance. That's our task. Let me make it look a little clearer to you. The wave function, delta phi, Yeah, and we got these, I guess, with the twiddle variable at this stage, I'm just saying it's proportional to the exponential. It's our random variable, and then its variance. Okay. So if we come back here, the regular harmonic oscillator written in terms of x and p with mass m, frequency omega, does anyone remember what the variance is of the ground state? So x squared. Remember what the harmonic oscillator variance is? It's okay if you don't. Let me just remind you, it's something like 1 over 2 m omega. Okay, well, it's h bar. I'm going to set h bar equal to 1 from now. Is that okay? H bar, right? It's due to quantum mechanics that there's any fluctuations at all. But it goes like 1 over 2 m omega. All right. And so similarly, we know what the ground state of this thing looks like. Well, wait a minute, sorry. Let's be a little careful here. Now back to Tony's issue. This is a fact when m and omega are constants, the standard theory. Okay, so let me just say, we're a bit slippery here. So if A were a constant, which of course is not the case that we are interested in, let's just, as a starting point, we'll call it AC for constant, just so we can get our bearings, okay? If A were a constant, then it's just the harmonic oscillator, standard harmonic oscillator, however you cut it, okay? And with this mapping. So I just insert, if I want, what do I call it? Delta phi twiddle, the variance of the field, is I just plug in the same formula, and I just insert this m and this omega. So we get 2k a squared. Okay, for the constant example. Okay, so that's the variance of a field. So far, this is just the variance of some field. Yeah, if you were to ignore expansion. Now, I wish to come back, therefore, to our original variable, delta phi hat. And remember, all I did is a rescaling with respect to root v. Okay, so if I put that back in, let's just delete it here. That means there's a volume sitting there. Okay. So from last couple of lectures, maybe you recall, maybe 2 lectures ago, we said that the variance in k-space is essentially the power spectrum. Okay. The variance in k-space was up to a volume factor, what we called P of k. That is the variance. That is the power spectrum. Okay. So this prefactor here is therefore the power spectrum. But this P here, I should maybe label it P sub phi. It's the power associated with phi. That's not necessarily the same thing as the power associated with density perturbations. They will be proportional to each other. Okay, but for now, we don't know we have to do some work to connect them. Okay, so the power with the field phi, essentially some rescaled variance, is this thing here. Okay, this is for a constant A. This is not great. The whole point is that A is growing exponentially. Okay. So unfortunately, we're like maybe 1 lecture short of doing the proper case. So I apologize. But maybe you could imagine now going back and allowing A to be a function of time, namely this function, and then trying to recompute the structure of the ground state in this theory. Okay. So one way you can think about it is the following. Imagine you thought that A was almost a constant for a while. You would write down the exact same formulas, and then you'll imagine it starts to evolve. So if you thought that it was initially a constant, you would have there would be such a thing as the ground state. You can talk about eigenstates of a time-independent Hamiltonian. and this would be it. Then when you take that state, which is definitely a Gaussian, and you say, aha, how would that state evolve now that I consider the fact that A is actually a function of time, namely an exponential? And you can track that state. Well, let me at least tell you a couple of facts if you don't know, is if you start with a Gaussian, it remains a Gaussian. It's a nice fact. So even though the effective m and omega are really now functions of time, okay, a Gaussian gets mapped to a Gaussian. That's the first fact. So this is really true, that it's still a Gaussian. Okay, but the variance changes. The variance knows that the m's and omegas are changing with time. We can already see it here, right? We have this thing as a function. It looks to go like 1 over a squared. So you can imagine, well, if I now promote a to be an exponential, well, it looks like there's a term here that's decaying exponentially. So that piece is true, but you get another term. So maybe I'll just quote it for you. If we had another lecture, we could derive all of that on the board. But does everyone understands the basic idea? Yeah, it's just a slightly time-dependent Hamiltonian, which is a fun little exercise. Okay, so now with a proportional to the exponential, let's just say you can show the variance of this effective ground state. Well, let me just write out power. So the ground state is still V times the power, and the power becomes 1 over 2k a squared. That much hasn't changed, but you get a new piece, which is the Hubble parameter, which I'll write HI. Yeah, Hubble during inflation over 2k cubed. Okay. A quick way of doing this, well, it's not that quick, but one way of doing this is actually you go to the Heisenberg picture. In the Heisenberg picture, you solve the equations of motion are linear because we have a quadratic theory. So equations of motion are linear. And in the Heisenberg picture, you just solve the classical equations of motion, if you recall. So it's not too hard to solve these linear equations. And then you can use that to build the variance. Remember, this is the variance up to a factor of V. Oh, and this kind of state is ground state. In this context, this is called the Bunch-Davies vacuum. Okay. So in field theory, right, the ground state is somehow the vacuum. Like this would be the honest to goodness vacuum if we were just sitting there. I considered this state around that point. Here we're sort of not quite in a vacuum, we're really expanding exponentially. So it's somehow a cousin of a regular vacuum that these authors wrote down many years ago. But as I said, it plays the role of a kind of ground state because the excited states get depleted, get washed away exponentially fast. So there's some sense in which it's also a lowest energy state. All right, any questions about this? Yeah. Yeah, from this point of view, we just have a Hamiltonian with some A of t's floating around that are explicit functions of time. And we literally have to just compute the properties of that harmonic oscillator with an m and omega, effectively, that are functions of time. We have to redo the calculation. Okay, and so when you just do that calculation, you get this. Right? So if someone handed you the harmonic oscillator, they never said the words expanding universe, but they gave you m as e to the ht, whatever, and omega is e to the minus ht, or whatever they are, and you just recompute, this is the variance, but written in terms of m's and omegas, and I just rewrite it in terms of k's and h's. Is that all right? Yeah, but of course it's the background that's providing A is e to the ht in the first place. Does that answer it?
Yeah.
All right. So if we look at this thing here, right, we can ask which of these two terms is most important. So this P, the power, right, write that. So you see it's this first term, 2ka squared, when somehow k is big, right? This term beats that. And that's in the regime, you can see when k over a is much bigger than h inflation. Okay? That's the regime where the first term dominates. And this has a physical meaning, right? Because this is what we call the physical wave number. The honest to goodness wave number of the mode that you're interested in is k over a. This is the co-moving k over the scale factor. And so when this is big, you just get the usual term, if you like. Okay? So these are modes that are therefore, remember this is 1 over dh. So these are the short wavelength modes. They're short compared to the Hubble scale. Yeah, so this is Hubble. These are the really short wavelength modes. So they have this kind of standard looking term, right, that we would have got had we ignored expansion altogether. So the short distance modes shouldn't know that there's this big universe out there that it's expanding. They don't really care about that. Their variance is the standard variance as though the universe was not expanding. It's the exact same formula. So it's the other limit where they know. It's the other limit where we get a completely different answer. So this is the important term for cosmology. This term dominates when the physical wave number is much less than the Hubble scale. Okay, so this second picture down here, if this is the Hubble patch, okay, this is where the wavelength is gigantic. Okay, so these huge wavelengths, they're bigger than the Hubble scale. They know the universe is expanding. Okay, so they get a totally different answer that you would get in conventional sort of flat space-time computation, which is this thing. They jump to this new formula. Okay, so our modes can begin their life potentially here, very short distance modes you can imagine, and they're all just getting stretched over time exponentially fast. So whatever mode you start with, it will evolve from here to here, right? Because the modes are stretching. Does that make sense? So every mode is going to end up in the second category if you wait a little bit of time. Does everyone agree with that? Or said differently, if we just go back here, A is increasing exponentially fast. So you see this term is becoming negligible. And very soon, all modes will just see this term, which physically is because they stretch to become bigger than the horizon, where they're governed by this term. Okay. Maybe we can have a little plot of, again, our length versus time. So we did this a couple of lectures ago. If you recall, right? So if you consider a physical wavelength, physical wavelengths always grow with the scale factor, right? To just stretch. And we've talked about how the scale factor, right, is t to the 2/3 in matter era, t to the 1/2 radiation. But now it's e to the ht in this inflationary era. And we can compare this thing to the Hubble length, is 1 over h. And remember, Hubble in these eras, this would be 2 over 3t, so essentially 1 over t. Oh, sorry, you flip that so you get t in the matter era, approximately t in the radiation era. but it's a constant, HI, constant in the inflationary era. Okay, so if I draw for you the Hubble length, and here's where the universe becomes, well, let's say let's plot this one. So first we have inflation, and it's a constant. And then it basically grows linearly in time, roughly. Inflation, radiation, matter. And on the other hand, so this, I'm trying to draw for you DH, the Hubble length has this evolution. Whilst if I plot a particular wavelength, how it stretches in time, you see in this era, at first it grows exponentially. So it's going to go somehow like this. And then it grows as a power law, but it's a slow power, t to the, say, 1/2 or t to the 2/3. So it's going to then go like this. So this is, say, some mode, I don't know, lambda, yeah, some particular mode of interest, a physical wavelength. So all the wavelengths are going to do this kind of, have this type of behavior. Okay, so back here, this means the wavelength is smaller than the Hubble length. That was that picture. They grow and grow. They become as big as one another at this point. They stretch, become way bigger. So that's this picture. And then when you enter the radiation matter era, it completely changes. And then they come back in. So this part of this picture we drew a couple of lectures ago. So out here, you're outside the horizon. Big wavelengths. And then you come inside the horizon. Okay. And you start off, if you keep going back, it's becoming exponentially tiny. It says that you start off inside the horizon. There's microscopic modes, incredibly small back here. There's a huge exponential expansion outside the horizon, and then it comes back in. So if you look at the value of the power, which is proportional to the variance, right, at, say, in this era here, well, somehow it's just given by this piece here. So you notice this thing is a constant. Okay, so this is why we can say, and I said it a couple of times in the course, when the modes are outside the horizon, we say they're frozen. Because this thing, right, depends on time, but this piece does not. Okay, so the variance, once you get here and beyond, it's stuck at the same number, and then eventually changes. Okay. So we have to connect this to the 10 to the minus 4. I haven't told you how that's related to the 10 to the minus 4. We're coming to that. But relatedly, let me just say, since I have the picture there, somehow this is going to give us a 10 to the minus 4 in standard deviation. And it's going to be frozen at 10 to the minus 4. And then when it re-enters the horizon, then it can start to grow. So it can become 10 to the minus 3, 10 to the minus 2, and so on. Okay. We talked about how density perturbations grow inside the horizon, right? Log in the radiation era, linear in the matter era. So that's all that stuff there. But here they're all frozen at this 10 to the minus 4 at this, with this variance. Does that make sense? So questions about this? All right. So let's see, how much time do we have? All right. Good. So let's try to connect to the 10 to the minus 4. Okay, because this number is, first of all, this number has units. So this number does not equal 10 to the minus 4. We have to relate it to the density fluctuation. That requires a little bit of thinking. Okay, so first of all, let's look at the standard deviation somehow in phi on scale k. Okay, so we did this, if you recall. Well, yeah, we did this. You recall, we have to like do some rescaling by some k cubed over 2 pi squared. So if you recall, there was this thing I called delta of k, and it's k cubed p phi k. This is delta for phi, the scalar field. You recall that? You can't just take the power spectrum and declare that's the variance. If you want to know what's the characteristic fluctuation on a scale k or to some size of interest r, you need this k cubed over 2 pi squared, as we discussed a couple of lectures ago. Is that all right? So that's somehow honest to goodness. Well, that's the variance, and the standard deviation would be the square root of that. Because that's just a general statement. That gives you the real standard deviation in a field on a scale k. Okay, so it has, if this is the standard deviation of the field phi, this has units of phi. It's literally the fluctuations. Okay, so this is basically, you could call this delta phi if you like. Delta phi. Okay. It's the standard deviation of delta phi. All right. So let's see. So outside the horizon, or if you like, essentially for every mode, once you wait, just wait a little bit of time, every mode will end up taking on this value, because that term, as I said, gets exponentially suppressed, right? Every mode ends up in this category. Is that all right? So this is the value we are to insert. So I plug it in here, and you'll notice not only is this a constant in time, the k's disappear. See, it was not so obvious that the k's would disappear. Sigma phi is then so this is h over 2 pi. So this is the standard deviation in the field. After all that, it's just h over 2 pi. Well, I won't go into it, but turns out the de Sitter space has a temperature, which is exactly that formula as well. That's not a coincidence, but I'm not, we don't have time to discuss that here. Just like a black hole has a temperature, de Sitter space has a temperature of this as well. So anyway, so you notice two things have happened. Not only is it time independent, okay, so it is time independent, or we say frozen, it's also scale invariant. Okay, because the k disappeared. Okay, so every k mode is stuck at the value of h over 2 pi, h during inflation. Somehow stuck at this value. All right. Now these are just the fluctuations in the field phi. Okay, so phi, we said h bar equal to 1. You can trust me, phi, a scalar field has units of Hubble. Okay. There's a big number if you were putting units of GeV, because we imagine the Hubble scale is really big. Okay, but anyway, it's some fluctuation in the field. But we need to convert this into density fluctuations. Okay? It's a bit abstract to talk about just the fluctuation in some funny field phi, and how does that manifest itself in density perturbations? Okay? Physical density perturbations that we can measure, especially given that this field just disappears. Right? So once you enter the radiation era, the universe is not full of phi. Phi decays into stuff, like we mentioned last time, for example, decay into fermions and so on. But at this point, phi has kind of disappeared, and everything, it all gets converted into hot stuff radiation. So we have to convert it into stuff that's relevant to the later universe. Okay, so this is another whole lecture in and of itself, but I can give you the quick way of thinking about this. Okay, so our task is to convert that fluctuation into a density fluctuation. All right. So any questions? So here's a picture we can have. Let's go back to V versus phi. And we have this potential, again, almost constant, but has a slight slope. We have to talk a bit more about the fact that there's a slight little slope to it, right? And here's, let's say, we'll call this one phi bar, the function of time. And it's going to, as I said, slowly roll down this potential. And at some point, maybe here, let's say, it starts oscillating and it dumps its energy into radiation. Okay, so down here, we have like phi goes into fermions or whatever it does down there as it oscillates, as we said. So for simplicity, just imagine it rolls, and then at some moment, bang, it just decays, okay, essentially instantaneously. Okay. So you can generalize all these arguments, but this is just the simplest case to consider. All right. So there's this spread, as we said before, of phi values. There's a spread delta phi. And delta phi means, again, the deviation from the mean. So phi is just the mean value plus its perturbation. And the standard deviation of these fluctuations is literally this formula here. It's h over 2 pi. Okay. That's just the width of the Gaussian. Okay, so that means if you consider some, say, random, say this is region of space, I don't know, 1, and another region of space 2, space now. The field value here, right, is just drawn from a Gaussian, and the field value here is drawn from a Gaussian. So they may take on different values, right? Typically, they deviate from one another by an amount of order delta, h over 2 pi. Okay, so to indicate this, let's just imagine, I don't know, here's the value 2. It happens to be, say, that number. And region 1 in space happens to be this number. Right, just randomly. Okay. Different regions are going to have different phi values with that standard deviation. Okay, and so then you can imagine, let's say you're in region 1. Right? So the field value happens to be here at some moment in time. It then rolls, and it takes a certain amount of time to get to the end and then dump its energy into radiation. Okay. So let's say, it takes I don't know, 100 in some units to do that, 100 inverse Hubbles to do that. But in region 2, it's starting up a little further. Okay, so it's not going to take 100 in some units to get to the end. It's going to take, say, 100.2 to get there or something, right? It's going to take a little bit longer because it has to travel further. So what we can talk about is the fluctuations in the time to end inflation. We'll call it delta t to end inflation, or to begin the radiation era. Because the moment you're here, I'm saying, bang, you become radiation. So that, I claim that delta t is then, the first approximation is delta phi itself over phi bar dot. Okay? Right, this is just like saying the time is distance over velocity. Okay? Is that all right? So phi bar dot is the rate at which the mean value, the whole thing is just moving along, and region 1 ends first, and then region 2 ends. And the little time delay from region 1 or region 2 is just proportional to the distance between them, delta phi, divided by the rate at which they're rolling down. Is everyone okay with that? Questions about this? And what we're saying is in position space is delta phi is a fluctuation throughout space. So you can think of this as a function of position. So too, there's a function of position. Okay. So different patches of space, therefore, will end inflation at slightly different moments in time. And this is the delay in time from one region to another. Okay. And the standard deviation for delta phi is h over 2 pi. Okay, then this thing, we need this thing to convert to density, to radiation. So I'm going to imagine instantaneous conversion to radiation at end of inflation. So that means that because they're a pair of regions in space, the time at which they end is slightly different. That means this region might start its radiation era now, and then a few moments later, this region begins its radiation era. Okay? Now, in radiation, the density is no longer constant. The density is dropping, like 1 over a to the 4. So that means if this one begins the radiation era a little earlier than that region in space, its density will drop a little bit more than this region drops. Does that make sense? Because this is delayed. Any questions about that? Okay. So the region that begins radiation earliest will then drop. And the region that begins later, it's in the inflating region for a little bit extra, and then it starts dropping. Okay, so this region would end up less dense than that region. Does that make sense? So let's look at how it is. We can just see this mathematically. So let's look at the energy density. Rho can be a function of space and time. That's what we're interested in. In this formalism, what you can imagine is that rho is a funny thing to write. We can write it as its mean value, which we think of as a function of t. But in this way of doing things, what we're saying is the time evolution for these two regions is different. One is delayed relative to the other. So in region 1, you just start there and you go on some history and then you become radiation. And over in region 2, it does the exact same thing, it's just delayed. So it just starts up there and then does the exact same thing with all the t's shifted by a small amount. So we can write this as t plus delta t. It's a funny expression. The full density distribution is kind of the mean value, but with a time delay or a time shift, depending on where you start in the potential. Okay, so if this is small, we can Taylor expand and write this as rho bar of t plus rho bar dot times delta t. Okay, it's first order Taylor expansion. And we should recall something about the background. This is how rho bar changes in the radiation era. Okay, we transition to radiation, and I need to know how much this thing has diluted relative to that one. So recall rho bar dot is minus 3h rho bar plus pressure. So this is minus 4h rho bar for radiation. And because radiation has P equals 1/3 rho. I mean, this is just a glorified way of saying rho declines as 1 over a to the 4. That's all that 4 is. Okay. So I just insert that in here. So you get rho bar minus 4h rho bar delta t. Are you okay with that? I just got rid of this. And then the rho bar I can factorize 1 minus this. Okay, so this is our rho. And so this is the mathematical version of what I was saying. If two regions are delayed slightly relative to each other in terms of when they begin diluting, there will be a density difference between them, which is this factor here. Okay. The deviation from 1, this is exactly what we call our density contrast. delta. Okay? We always write this as rho bar 1 plus delta t in x. So therefore, our delta, well, let's say delta of x is minus 4h. This is essentially the end of inflation, delta t. Okay. So that is a quick way to connect this to a density perturbation, right? So these are the three steps in the logic, right? This was the sharpest calculation perhaps in today's lecture, that the fluctuation in the field, the scalar field phi, the inflaton, is Hubble over 2 pi. That manifests itself in the fact that different regions end at different times, delta t, and that manifests itself in a density perturbation because different regions are diluting at different times, and therefore there is a density contrast between them. Okay, so we just plug this delta t into there, and then we plug in the standard deviation. So let me squeeze it in here. This is minus 4h delta phi over phi bar dot. Okay, and here's our standard deviation for phi. So if I ask you what's the standard deviation in density contrast, right? That's what we want. It's literally, I mean, the standard deviation of this variable. Well, the standard deviation in that variable must be standard deviation of positive quantities, by the way. So these minus signs don't matter to the standard deviation. Right? I mean, this variable here fluctuates between positive and negative values. So that minus sign doesn't affect the standard deviation, right? Standard deviation is by definition positive quantity. And in fact, even the way I've drawn it, I guess phi bar dot is negative. As minus signs cancel anyway, but it's not so important. So I can write this as 4hi over, I guess, the magnitude, because again, this is standard deviation, times the standard deviation in phi. Okay, the standard deviation in the density contrast is some prefactor times the standard deviation in phi, right, from this formula. Does that make sense? Fluctuations are proportional to each other, so their standard deviations must be proportional to each other. Oh, and I should also emphasize, since we already said that the fluctuations in the field phi are Gaussian, because that's the ground state, because this is just a linear relation here between delta and delta phi, it must be that the fluctuations in delta are also Gaussian. Okay, so yeah, this is also Gaussian, which is what we actually care about, is the density perturbations. And so now we just plug in this formula, h over 2 pi. So we get, let's see, 2 over pi h squared over phi bar dot. That's the standard deviation in the density. Yes, was there a question?
Yeah, so is this relying on an idea that phi bar dot is roughly constant?
In my approximation, yes. I'm imagining this is like has a essentially linear. So from the beginning, I even threw away v prime prime. So that's strictly true in the limit where, you know, it's a linear function. And a linear function, this is basically a constant throughout this era. And then it will rapidly change as it dumps its energy into radiation. Okay, but here it's roughly constant. That's right. Other questions? And so finally, this is the number, okay, just to be clear, to match observations. This is the thing that has to be, right? This is the thing that I said was 0.5 times 10 to the minus 4. Okay. here I wrote, well, at some point I wrote 10 to the minus 4, but 0.5 times 10 to the minus 4 is the precise value. Okay, so those are the fluctuations. They're just locked in at this value on super horizon scales. They're frozen at that number. And then they enter the horizon and they grow. Okay, so the funny thing is that this slightly oddball combination of quantities has to equal 10 to the minus 4. And that thing has to be that. Okay. And let me just put in maybe the corner here. So let's recall the Hubble scale, right, is 8 pi g over 3 times the energy density during inflation. And the energy density during inflation is almost all potential. So this is the potential V. Okay, V during inflation, I could write. Right? That means the height of this potential. Okay, so the height of the potential, up to some 8 pi g over 3, this numerator is just the height of the potential. Okay, so that's what's controlling the numerator. The denominator is controlled by the time derivative of how quickly or slowly this field rolls down the potential. And for the denominator, we take the equation of motion, right, which is phi double dot minus plus 3h phi dot. Let me just write down the full equation of motion that we wrote down last time. Yeah, that's the equation of motion. But this is the background. This is a statement about how the background rolls, the mean value. So the background doesn't see this gradient term, so that's not there. And furthermore, when things roll slowly, okay, if you're rolling slow enough, you're in the sort of friction-dominated regime. It's rolling so slow that actually this acceleration term is negligible. Okay. So it's kind of like something in terminal velocity. It's rolling at some phi dot. So you see phi dot on the background is basically minus V prime over 3h. Okay, so you can insert these formulas back in here. I won't bother doing that, right? But you can see that the time derivative is related to the derivative of the potential, and Hubble is related to the value of the potential, right? So maybe, well, why don't we just put that? If you do those little substitutions, very easy to put them in, and you can rewrite this explicitly in terms of the potential, purely the potential. And you get some funny 2 over pi, well, there it is. And then if I did this right, divided by V prime, magnitude. Okay. Yeah, so that means, that just shows you that everything's completely controlled by the potential, the height of the potential and its derivative. That weird combination of things must equal 0.5 times 10 to the minus 4. Okay, so this is what we know about the inflationary potential. It's a weird combination of things. And we don't know a whole lot more than that. Okay. Questions about this? All right, so let's see. So next Wednesday, remember, is the first day of presentations. Okay, thank you.